Okay, so let's get started. So today we will discuss the chapter 5. So chapter 5 is more computational methods. So chapter 5 is about resampling methods. So we discussed the one is the cross-validation and the Bootstrap. So how many of you have heard of cross-validation? Maybe Bootstrap. Okay, good. Okay, so maybe we can spend a little more time on cross-validation. So cross-validation is probably the most powerful method to estimate the test performance. So in statistics, we have two concepts. One is the training error or training performance, and the other is the test performance. So training performance is that for example, we use the 100 observations to fit some statistical model, and we use those 100 observations to see the performance of the model. But since we have already used those 100 observations, that is logically nonsense, right? So the better way is to prepare a test set. So we construct a model with training set, and we prepare the test data set to evaluate the performance. But always we have some drawback if we use the training test approach that is called validation approach, because suppose we have 200 observations in total. If we use 100 observations in training set and the other 100 as test set, we can only utilize the 100 observations to fit the model. So even though we have 200 observations, right? So we have to solve that dilemma to get a better performance. So that is the method called cross-validation. And the Bootstrap is another idea. And maybe, okay, so I will share the screen to start. So Bootstrap is basically the methods to evaluate the variability of the data. So when we calculate some variability, we calculate some, for example, prediction performance. For example, we got the AUC of 0.9 from the binary prediction problem. Then how accurate that 0.9 is? So we have to have some methods to evaluate how reliable our estimate is. So that is the so-called the Bootstrap. And both are based on so-called resampling methods. Resampling method, okay, so maybe I share the screen first. Okay, so resampling method. So resampling method is just we sample from the sample. So suppose that we have 5 observations, such as, okay, so 1, 3, 7, 10, 5. We have 5 observations, but the resampling means that we sample from these observations. For example, we take 1 and 10 and 7. So we resample from the sample. Sometimes that we allow the duplications, for example, the 1 and 5 twice, and 1, 10, and 1 again, or something like that. So this is basically the meaning of resampling. And you can see when we do resampling that we have some randomness in resampling. So that helps us to evaluate the randomness of the data. So it's very novel approach for data analysis. Even we have 5 observations, we resample from those 5 observations. Right? Yeah, in some sense, if you play computer game, sometimes if you play some game against computer, then the computer does not always move in the same way. So that means the run that is caused by some randomness, right? So just you are played by computer with some randomness. So it's a kind of similar situation. So resampling method is statistical method to sample from existing data set. So it is useful to evaluate the variability of data and variability of estimated statistical models. Yeah, for example, the also linear model. Suppose we fit the model y is equal to a plus bx. Then you estimate a and b. Okay, so suppose that the estimate is 0.5, the b is equal to 1.2. Then how reliable this 1.2 is, how reliable this 0.5 is. We have some theory, and for example, the R outputs return the standard error of this. For example, standard error is 0.6 and standard error is 0.1. But that is based on many assumptions, such as error follows normal distribution or errors are IID and so on. For some complicated methods, this is more difficult, and sometimes it's not realistic to theoretically calculate these standard errors. So we rely on simulation methods to estimate these numbers. So that is our topic. And the one is the cross-validation. This is a method to evaluate test errors with the multiple randomized training and test sets. And the other is Bootstrap. This is a method to estimate distribution of parameter estimates with multiple sampling from the dataset. So cross-validation is for prediction performance. The Bootstrap is for reliability of parameter estimates. And at first, before we do resampling approach, we review our validation set approach. So that is basically that we split the original data into two sets. And okay, so the blue one is training set, and the next one, the orange one is test set. And we use training set to fit the linear model, for example. Then we test the prediction performance with the test set. So that is the approach. And usually these are randomized. If we have n independent observations, these are just randomized. If the n observations are independent. So this is the simplest case. But sometimes, for example, time series data, the time structure is important sometimes. So in such a case, this may be the first half of the period, and this is the second half of the period. So that is also possible. And also, if observations are not independent, for example, we have 100 observations, but actually the 5 observations are from the same individual. For example, we have 5 blood pressure measurements from the one patient, and we have the 20 patients of data. Then in such a case, usually that we split, the 10 patients and the 10 patients. So 10 patients for training set and 10 patients for test set. Then we can see, for example, dependency of the observations within the patient. If we entirely randomize, sometimes it's a problem. Yeah, but for independent data, just randomly split the data. So if you use, for example, some sample data in R, and if you just take the first half and the last half, then if those rows are not randomized, you may have some trouble. Yeah, and what's the problem of this, the very intuitive, the training and test approach? If you estimate this, then you encounter many problems. And the typical problem is, the fundamental problem is the trade-off between the accuracy of the statistical model and accuracy of test error. So suppose you use like 90 observations as training and 10 observations as test. Good thing is you use most of the information to fit the model. But you have to evaluate the performance of the model. And if we only have 10 observations to 10 observations to evaluate the model, then that is just a gamble. So it really depends on the characteristics of these 10 observations. So that means probably the model is accurate, but the accuracy of test error is low. So the estimated model is more accurate when training set is large, but the test error is less accurate since the remaining test set is small. And the small training set and large test set makes the opposite problem. So if we have 10 observations for training set, it's really hard to get a good estimate. If you fit a linear model with 10 observations, it's really not reliable result. But the test set, we have 90 observations. So test performance is evaluated more stably. So we have trade-off, and you wonder how many observations to take. I think that if you have to take this approach, then I would use maybe 2/3 of observations as training, or maybe 70%, 80%. That is probably a fair number. For example, time series data, sometimes we have to do it in this way. Yeah, but anyway, so we have the trade-off between the accuracy of model and accuracy of test error. Yeah, and here is one example of the fact. And the data set is divided into training set and test set randomly. Yeah, it does not say the details, but maybe we split the original data set into 50% and 50%. And this randomization produces variation in test error. Okay, so we fit with the training set and we calculate the test error. So we separate the data into two, training and test, but each time we use different random numbers to split the data set into these two sets. So based on these, sometimes the error size is small and sometimes error size is large. So yeah, you can just focus on some section. So this is the degree of polynomial. So basically we fit y is equal to b0 and b1x plus b2x squared plus epsilon. Then we calculate the test error. And this is just one training and test set, but we do this 10 times with different randomization of training and test sets. Then actually the performance varies a lot. So unfortunate case, the error is always very large. Mean square error is about 25, but if we are lucky, the error is always small. Also, the optimal model is different. For example, you can see that this case, the thick orange, the line graph, probably 2 degrees of the 2 is the best, the number for degrees of freedom, but the degree of polynomial, but for maybe this yellow one, probably 7 is the best. So the model choice may be different depending on the data set. So it's not really stable, especially if you want to see the true expected, the mean square error, our estimate isn't really reliable. It ranges from, for example, 16 to 25, 24 maybe. So that is the problem. Yeah. Do you have questions so far?
Yes. I'm just looking at this training set, and I just want to make sure I'm looking at it. Are we taking basically 10 random using the same percentages, say 50-50 or whatever
yes,
it happens to be?
Yeah, I believe so.
Side?
Yeah.
Okay. And Oh, that makes a big difference. If those
Yeah,
are,
it makes a big difference. So why this happens? For example, suppose we have 100 observations of xy. So xi, yi, I is equal to 1 to 100. And suppose only one outlier. For example, the x50, y50 is an outlier. And if this outlier is included in the test set, probably the mean square error, the test mean square error is much larger because outlier is not predictable. Of course, the outlier in a training set has some negative effect, but as long as this doesn't have really large leverage, then probably it does not affect the estimation result much. But if this is outlier in a test set, then the test error is larger. So probably this variability means that we have several outliers, maybe, then this can happen. No outliers and the model is very good, then probably we don't have this much difference between randomization. But this is often the case. So model performance really depends on which observations are in the test set. Yeah, so it's surprisingly large variability. So it doesn't specify how many observations are there, but I think this is the horsepower in the auto data. So probably only hundreds of data, maybe points. I think this is library ISLR and the auto data set. So this is 392 observations. And I'm not exactly sure how many are in the training set and how many are in the test set, probably half and half. So 392 observations. Yeah, you can play with the data to see how much variability it has. Yeah. So the problem is, as I discussed, it really performance depends on which observations are in the test set. Okay, so predicting outlier is difficult, but predicting the usual observations are easier. So next approach is cross-validation. So this is basically the most accurate cross-validation, that is leave one out cross-validation. So the idea is here. So we have data set, and the blue one is training set and orange one is test set. So at first, we take just first observation as the test set and the other n-1 observations as the training set. So we fit a model, for example, linear model with training set with n-1 observations. Then we evaluate the performance with just this one observation. So yeah, so that is possible. Of course, it really depends on what observation this is. And we repeat the same procedure for other observations as well. So that means just second observation as the test set and the other n-1 observations as the training set. And we repeat n times. So we fit basically linear model n times. So if we have 392 observations, we fit the linear model 392 times with 391 observations each time. Then we calculate the error size, maybe average the square the error size. So this approach is very good because each of the observations are used as the test set exactly once. So we don't have any variability. We don't have any variability. So that is very good. And also, we didn't randomize anything. So training and a test set approach, even you can make a trick. If test error is too large, you can resample it and again and again and to make it the test error smaller. So that we have some arbitrariness. But here, we don't have any arbitrariness. So we try just all 392 models, and we don't have any randomness. So it's very objective method. So this is leave one out cross-validation because we only leave one observation out as the test set. So to be concrete, this is the procedure. So suppose that x1, y1 to xn, yn are observations. Maybe xi's are vectors if we have multiple predictors. Then LOOCV, leave one out cross-validation, splits the data set into training set with n-1 observations and the test set with ds observation. Then suppose that xi, yi is the test set. Then we estimate the model with the training set and let yi hat be the predicted yi. Then the test error is just the square of yi minus yi hat. Then denote this as MSEI. This is the ith mean square error. Then we repeat this the n times, 392 times in the last data set. Then we calculate the MSE sub I for all possible I. Then they calculate the average. So that is the MSE. That is the cross-validated error. So cross-validated mean square. Maybe we can see CVMSE.
So this works really well to identify an outlier.
No, so my claim is that this method is good to accurately estimate the test error. So expected error size for test set. So the point is that, okay, so we have 392 observations, right? And we fit the model. Then we have, suppose, another new data set with 10,000 observations. Then it will have some mean square error, right? So this is the expected mean square error in the sense that the sample size is large. And to estimate this MSE, this cross-validation approach works well. Yeah, so ideally, we have the training set, we have the large test set. Like we have 92 observations now, and next year we will have 10,000 observations. So we want to construct the estimation model this year to apply the future 10,000 observations. And how good the model is, we want to estimate the accuracy of the model. And this cross-validation is basically the best method to estimate the expected size of MSE. Yeah, maybe another way to put it is, okay, if we take the validation approach, that we have training set and the test set and maybe future large data set. And training error, training MSE, this is usually the underestimate of the future data, future error. So future error, suppose we have very large N. So we want to calculate the expected value of MSE, but the training MSE is usually biased because we use the data set itself to predict that data set. And test set, the test MSE is usually unbiased. This is around the expected value of MSE, but the variance is large. So we want to estimate this expected value of the MSE in a better way. So that the answer is this, the leave one out cross-validation. Yep. Any other questions? Okay. And again, here I summarized some pros and cons, a little more detailed explanation. So leave one out cross-validation. One good thing is the training set is large. So estimated model is as accurate as the estimated model with all observations. So that is the bias of the cross-validated error is very small. So it's a little bit hard to understand this, but we want to use 392 observations to develop a model. Then we want to estimate expected size of MSE, right? So basically, we want to use all observations. We want to use all observations, right? So we want to replicate this, situation, the estimating the model with 392 observations. And basically the leave one out cross validation is using 391 observations to predict the other one, right? So estimating with 392 observations and estimating the model with 391 observations. So these are really similar. So model accuracy is almost the same for these two models. So this is different for the validation set approach. Suppose we use 196 observations as training set and 196 observations as the test set, then we have to estimate the model with only 196 observations. So data size is just half. So that means the estimation result is less reliable. So that means this model is worse than the actual model we estimate with these observations. Yeah. So this is basically too difficult to predict. So, but the leave one out cross validation almost replicates the situation that we estimate the model with 392 observations, and then get the expected size of MSE. Okay. And another good thing is the training set is large, so the model has less identification problems. For example, suppose that the binary predictor value is 0 for most observations and 1 for only a few observations. And if the training set is small, the predictor value may be 0 for all training observations, resulting identification problem for the coefficients of the predictor. So suppose that, for example, this is the car fuel efficiency data. And suppose that we only have the two hybrid cars. And maybe we want to estimate the two hybrid cars. Maybe that is too small, but maybe suppose two hybrid cars. Then we want to also estimate the how hybrid car performs better than traditional combustion engine. Then if we use training and a test approach, sometimes these two hybrid cars are both in the test set. So the 196 observations are all traditional the engine cars. So in such a case, of course, we cannot estimate the effect of a hybrid system, right? But if we use 391 observations as training set, then at least one hybrid is there. And also, most of the time, the two hybrid cars are here. So at least we can estimate the effect size, right? So that is another thing. So this is especially true if we have many variables, but some variables are sparse. That means the only takes non-zero values for the small number of observations. For example, housing market data. And the one variable explains whether or not that house has indoor swimming pool. Then indoor swimming pool exists in very few houses. So in such a case, the training and test approach has sometimes problematic. Yeah, and another thing is that there is no randomization in the method. So the leave one out cross validation is very deterministic process. So the very objective and no uncertainty. And why sometimes we don't use this method? The computational burden is large. If there are 1,000 observations, we have to estimate the model 1,000 times. Yeah, so 1,000 times. So so that's a lot of time. For linear regression model, that is very algebraically easy model, the simple model. Actually, we have a shortcut to calculate the cross-validated error, leave one out cross-validated error. And actually, it can be calculated as this. So this is very simple. All yi hat is estimated by just all observations, all training observations. But we have some denominator here, 1 minus hi. So we inflate this a little bit. Hi is a positive number. Okay. Then we can calculate cross-validated error here. And hi is basically the so-called leverage. Maybe it's adjusted by some constant, but the hi is 1 over n times this. Basically, this adjusts the standard error of this yi minus yi hat. So this is much different from method we discussed in the previous slides, because in the previous slides, so this yi hat is estimated by observations other than I. So to get one yi hat, to get one, so for example, y1 hat, we have to estimate the model. To get y2 hat, we have to estimate another model. But here, all yi hat are estimated by just one model. So only we have to fit the model once. So computational burden is just the same order as fitting a linear regression. So for linear regression, we can use this formula. We don't prove it, but we can use this formula. So always we can use the leave one out cross-validation. Okay. Then, okay, so this chapter discusses the resampling methods, but we don't have any randomness here. And why this is resampling methods? Then, actually, we have another method, so-called the k-fold cross-validation. And k-fold cross-validation is much faster than leave one out cross-validation. Slightly less accurate, but still the comparable accuracy. So the idea is here. So we fit the model only 5 times, not 392 times. So just that we randomly separate the entire data set into 5 the equal sized data sets, subset data sets. Then we use the first 1/5 as test set and the other as training set. And so this is one estimation, and we calculate the mean square error, maybe MSE1. Then second, that we use just the second fifth of observations as test set, and the other as training. So we fit with training set. Sorry. Yeah, we fit with the training set and we test with test set. So we repeat this procedure 5 times to get all observation used as the test set once, test data once. So still, okay, so we randomly split the data, so it has some randomness. So my result for this cross-validation and your result of cross-validation, 5-fold cross-validation, are different, but still, each observation is used once as the test data. So the variability isn't as large as the previously shown. So variability is pretty small. So this is called 5-fold cross-validation. So if we split data into 10, so this is called 10-fold cross-validation. Which is more accurate, 5-fold or 10-fold? To estimate the expected value of MSE. How many people think 5-fold is more accurate? How many people think 10? Okay.
I would guess it probably depends on the size of the data set, right?
Sorry?
would it depend on the size of the data set?
Actually, in terms of performance, the tenfold is always better. One reason is we can use 90% of observations rather than 80% of observation in fivefold. Yeah, but practically tenfold cross-validation takes twice as much time as fivefold cross-validation. So sometimes we have to opt for fivefold. Yeah. So that's the answer. Yeah.
Professor, I had a question about the you said the computational complexity is the same as linear time or as linear regression. Is that like is that asymptotically, right? Or is
yeah. I mean, yes, of course, the less observations, yeah, slightly shorter time. That's true. Yeah.
Okay. No. That's what I thought, because I think the shortcut is like quadratic time. I think I could be wrong about that.
Yeah.
I guess it's not really relevant. I was just curious.
Yeah. Yeah. So the linear model. Yeah. So it really depends on the model, but the linear model is okay. Suppose we have n observations, and the linear model is, if linear model is just y is equal to a plus bx, then just the time needed is order n. So yeah, order n. So the k-fold cross-validation, if we multiply constant, still order n. And leave one out cross-validation, n times order 2. So order of n square. Yeah, that's right. So in terms of order, the cross-validation has much less time necessary to compute.
Okay, that makes sense. Yeah. I think it's quadratic time.
Yeah, quadratic time of n in case of linear model. And if original model needs more time, then yeah, of course it takes more time. Maybe k and n with the k is equal to square root of n, then probably the computation time is large. But yeah, but the point is the cross validation does not increase the computation time. We only multiply some constant, but the doesn't make it larger times the time order of n. Yeah.
Okay, that was my question. Thank you.
Sure. Yeah, so usually in statistical model, the number of observation n is important to determine the time, and also the number of predictors p that matters for the time. And usually p matters more than n, so sometimes it's a problem, but we are still doing traditional statistics. So p is small, like 2 or 3, and n is large. So yeah, that makes sense to consider the time order of n. Yeah, so algorithm, yeah, I think almost the same, but the k-fold cross-validation. So divide the dataset into k-sized groups randomly, and use the ice group as the test set and the remaining k-1 group as the training set. We combine the other k-1 groups as the training set and evaluate the MSE. Let's say that is MSE1, MSE sub I, then repeat this step 2 for all i's, then we calculate the average. So that is cross-validated error for k-fold cross-validation. Yeah. And k-fold cross-validation, yeah, maybe we discuss how to choose k, but basically larger k is better, but more computational time. Okay, so first we see some examples. So this is the left-hand side shows original data. So the black curve is underlying the true regression curve, and the black circles are simulated observations. So basically, we know the truth. This is a simulated study. But from these observations that we estimate the polynomial. So we do polynomial regression. And the yellow one is the simplest polynomial regression. So we fit basically y is equal to beta naught plus beta 1x. But the others are more complicated. So the blue one is the 5th degree polynomial. So y is equal to beta naught plus beta 1x plus up to beta 5x5. And the green one, even larger. I think this is 20 up to 20. Y is equal to beta naught plus up to beta 20 x 20s. Then, which one is the best in a common sense? You can see that the yellow one is too simple compared to the truth, even the black circles. But the green one is too volatile. So the blue one is probably the most appropriate. And here that we see the result. So this one is training error. And this one is the test error. Actually, this is, I think, the expected test error. Maybe the expected test error square. Yeah, and okay, so we have some other cases. For example, next one. So this one is pretty simple. So maybe yellow one is the best. Maybe it's possibly blue one. Green one is too complicated. And you can see the training error here. So here, flexibility. So this is the degrees of freedom, number of degrees of freedom. And this is the test, this is MSE. Number of degrees of freedom means if 2, that means 2 parameters. So this is beta naught plus beta 1x. Y is equal to 5. Then we have 4-degree polynomial. So this actually tries the straight line and the quadratic curve and the polynomial with degree 20, maybe 21 or 2. Then MSE and the training error, of course, the smaller if model is more complicated, but the test error probably minimized, actually minimized here. So probably flexibility, I would say P is equal to 3 is the best. And again, this is actually the expected error size and expected MSE. So this isn't really cross-validated, but just I want to show the examples first. And example 3, again, the black one is the true curve, and the yellow, blue, and the green are estimated. And probably the blue is the best again. And you can see the test error, the blue one is the smallest. And this is the, the simulated study. So we can calculate the theoretical expected MSE. But okay, so how good the cross-validation is to estimate this. So that is seen here. Blue line is the true expected error that has been seen in the previous 3 slides. And the dashed black curve is the LOOCV error. So this is the best cross-validated method. Still, it's not the truth, but the what we can do best. And the orange curve is tenfold cross-validated error. So this is a kind of the second best method. I mean, not as good as LOOCV, but we expect this is almost as good as LOOCV. And you can see that the orange and the dashed black line, dashed black curve are pretty similar. Still, we have some discrepancy between the truth and our cross-validation, but in terms of comparison of the 2 cross-validation methods, these are really similar, and actually they select almost the same model, maybe slightly different, but I think maybe it's the same if flexibility is an integer. And here also the same for the second data set we have seen, and the third data set. Okay, so slightly different, but still errors are pretty similar. So, okay, LOOCV is the best method, but usually we don't really care. So to shorten the computational burden, just it's okay to use tenfold cross-validation. And in many packages, we use the tenfold cross-validation. Yeah, so once my student worked with the medical doctor to do some analysis, and they need to do cross-validation. And he did the 5-fold cross-validation. 5 is pretty, convenient. It's, at least, twice as fast as 10-fold cross-validation. Then, okay, so then we submit. Then the medical doctor concerns that many people use 10-fold cross-validation. And is it okay to use 5-fold cross-validation? And yeah, actually 10-fold is slightly better, but the performance doesn't change much. So just I convince her that the people use 10 because in many statistical packages, 10 is the default. But it does not mean 10-fold cross-validation is twice as accurate as the 5-fold cross-validation. It takes twice as much time. So 10-fold cross-validation takes twice as much time, but the performance is pretty similar. And how to choose K? Yeah, K, 5 or 10 is fine. Sometimes I use just 2 or 3 if model is very computer intensive, large neural network or something. Yeah, always you can start with small k. Then if you have more computational power, you can make it larger. And large k gives smaller bias because k is equal to 5. The test data set is 1/5, 10, 1/10. So that means the training. So test is this. So training is the 4/5 and the 9/10. So 9/10 is closer to 100%. So it's better.
Which,
So
what would, sorry, for K, special case of LOC, which is the best case, potentially if you can calculate it all the time. What
K is
is
equal
the
to n is the best.
K equals n? Okay.
Yeah. So K is 10, K is 5. Minimum is K is 2, right? Minimum.
Which is the similar to
Twofold. Yeah, training test approach, but at least we cross-validate it. Yes. So in terms of the worst, but the not much difference. Yeah. Yeah.
Thank you.
Sure. Yeah. Yeah, and of course, the large K has a large variance to estimate the test error because we have the smaller test set. But if we cross-validate and take average, then finally this problem disappears. So maybe we can just put this in a parenthesis. And yeah, and we have discussed the regression case, but also classification case that we can also use cross-validation. So we can just take the average error size. Error is defined by indicator function of whether or not yi is equal to yi hat. That is, error is 0 if classification is correct, and error is 1 if classification is incorrect. And if we have multiple classes like rating, and we have 1, 2, 3, 4, 5, we can even put some weight on the accuracy measure. So this is correct, this is correct, this is correct, this is correct, and this is correct. If truth is 1, but the predicted value is 2, it's a kind of close. So for example, we can give the error of 0.1, here 0.2, 0.3. So that is also a possible way to evaluate test error. So yeah, you can choose your performance measure to be consistent with your, prior information on the difference in categories. Yeah. So this is called the so-called weighted kappa. Yeah. So you can put some weight on the error. But yes, the simplest way is if classification is not correct, always we give 1 as the size of loss. Yeah, and here, okay, so more concrete example of the use of cross-validation. So we wanna do classification problem, so binary classification problem, and we wonder what model is the best. And we have the 2 predictors, x1 and x2, and we consider the polynomial of x1 and x2 to fit the response value. And we want to determine this k. K is equal to 1 is the simplest one, maybe 0 is also possible. K is 1, 2, 3, 4, 5. We can have increasingly more complicated model. We want to determine optimal k. So that means for each k, we evaluate estimated error size, then we choose the best k. So here, the degree 1, 2, 3, 4. And logistic regression is basically, logistic regression has the linear boundary if the linear case. So if predicted value, probability of y is equal to 1, and the inverse logistic function is equal to, beta naught plus beta 1 x1 plus beta 2, maybe beta is not good, maybe alpha 1 x2. Then boundary is linear. Okay, boundary means the 50% probability. So the probability of y is equal to 1 is 50%. The boundary is here. And here the purple, the dashed line, is the true boundary between these 2 classes, orange and blue. And the orange circles and the blue circles are observations. And our estimated line is the black line. So black line is somewhat reasonable, but of course it's not too close to this purple dashed line. And if we get higher degree polynomial of x1 and x2, but we don't actually include the interaction term. So, but that is our specification. Degree 2, degree 3, degree 4. And yeah, it sounds that, I don't know, maybe degree 2 is slightly better than degree 1, maybe. Yeah, at least this observation. So this observation is correctly classified in degree 2, but the degree 1, actually it's misclassified, for example. And the degree 3 and the degree 4, it's not exactly sure. Actually, we make larger error here and here, even though we don't have any observations. But yeah, in terms of this area, maybe it's a little more accurate than the degree 2. So it's not clear. Maybe degree 2 is probably better than degree 1. Degree 3 and 4, not exactly clear. Then you can evaluate cross-validated error, and that is here. So this is just the training and the test approach, the validation approach, and this is the tenfold cross-validated error. And yeah, so yeah, so the black one is the best indicator for the expected error size, so that we should opt for order of polynomial equal to 4. So that means the 4-degree polynomial is better. So actually this is better. So actually this is better than 3 to 1, but more than 5 or more, actually it gets a little worse. So in this way, we can select the model. Yeah. So alternatively, we can use, for example, AU's Akaike information criterion or something. But this is based on many assumptions, such as normality of data and so on. Like logistic case, the logistic function is correct, or some other, the assumptions. So this cross-validation does not depend on any assumption. So usually it's more robust against violation of the assumptions. Do you have any questions so far? So probably the best method, use of cross-validation is to compare different models. For example, neural network models, support vector machines. Those models do not have likelihood, while linear model has likelihood. So we cannot compare likelihood or AIC for those models. But the cross-validation, as long as we have the same objective, then we can compare the models. So that's good. So if you transform the y values by log scale or something, we cannot compare. But as long as the response variable is the same, we can compare any models. So that is the most convenient and powerful aspect of cross-validation. Yeah. So it does not depend on the model. Okay, so next method is Bootstrap. So Bootstrap is a method to estimate distribution of parameter estimates with multiple sampling from the data set. Okay, so just we go to the example first. So suppose that we have n observations, independent observation in a sample, and we want to estimate the parameter alpha, for example, population mean or population variance or slope of regression or something like that. Then this is the procedure for Bootstrap. At first, the randomly sample n observation with replacement. So if we have 5 observations, we can take 5 observations from those 5 observations, but with replacement. And calculate the parameter estimates, for example, say the alpha I hat from the sample in the step 1. And we repeat this many times. Usually not many times, not that many times. Maybe, yeah, when I was a graduate student, the professor suggested 300 times. If you have to publish some academic papers, then you may go 10,000 times, but not too large number. And yeah, but still large. And make a distribution of these estimates. Maybe I would say hat. Okay. Then we can get the distribution of alpha. So we can see how accurate this is. Yeah, so yeah, and yeah, for example, yeah, distribution, we can get the histogram of alpha hat. So yeah, we can get actually the distribution. But if we only want to know the variability, of course, we can calculate the variance by the sample variance of alpha. Maybe I would say alpha I hat. And this is the average of, so sample mean of alpha 1 hat to alpha b hat. Yeah, so I think it's good to have some examples because the abstract argument isn't really the best way to explain it. So sampling with replacement is here. So original sample is this 1, 2, 4, 8, 16. And if we sample with replacement, we can use the sample function with replacement option. It may be the 2, 4, 1, 4, 8. So we pick up 5 observations, but with replacement. So 4 appears twice, but 16 does not appear. So basic principle is that, okay, we only have 5 observations. So basically our probability space is this, and the probability is 1/5 each. So that is the basic idea. So in reality, of course, if we have more observations, that may be 7 or maybe 3.5. But since we only have these 5 observations, so the most, the natural way, I mean, if we don't assume anything more, then the give 1/5 probability for each observation is, a reasonable approach. So that's why that we do 5 observations with replacement.
Dr. Shinki?
Yeah.
How do you have a sample of 3.5?
I mean, for this one, this is observation. If we observe more observations, then that may be different from these 5.
Yes.
For example, yeah, but from this data set, of course, we cannot observe 3.5.
Okay, thank you.
Yeah. So just I want to explain that these 1/5 probability are not really the truth, but this is just assumption within this Bootstrap method. Yeah, and yeah, this is another try. So 16.8444. So example, suppose these 5 observations, 5.1, 4.8, 3.9, 5.3, 4.1, and calculate mean and standard deviation. So this is maybe high school level question. Then estimate standard error of the mean. So that is the standard error of X bar theoretically. Then estimate this standard error of the, that it teach the mean by Bootstrap. Okay, so at first, the mean and the standard deviation here. X is here, mean and the standard deviation. Mean is 4.64, standard deviation 0.614. So these are just descriptive statistics. And okay, so based on the assumption of these are independent, okay, so we have x1, x2, x3, x4, x5. Then our situation is the expected value of x is about 4.64, okay, estimated. And standard deviation, maybe I would say maybe xi hat expectation of xi. The estimate of expectation of xi is 4.64. Actually, the the expectation of x bar estimate is also 4.64, right? So x bar is equal to the x1 plus x2 plus up to x5 divided by 5. Then this says that the standard deviation of xi, this is equal to 0.6148. So this is again estimate, but the standard deviation of xi. Then what's the standard deviation of x bar? The standard deviation of x bar is actually 1 over square root of 5 of standard deviation of 1 observation. If we take average of 5 observations, then the variance becomes 1/5 times as large as original standard deviation. So if we take square root, that is 1 over square root of 5. So this. So this is, okay, so this estimate is 1 over square root of 5 times 0.6148. So that is 0.24727495545. Since we can use the independent observation assumption that we can deduct this, but this can be done because our model is very simple. So all observations are just independent, and yeah, and also the same variance. So we have IID assumptions, right? So all xi should follow the same distribution. So that makes this estimate. But if even without those assumptions, then we can use this. So still the Bootstrap is based on independent assumption, but we can, without using this theory, the Bootstrap method can estimate this. So this is the simulation method. So we iterate this 100 times. We sample 5 observations from X, then take average. So we have many averages. So maybe 1 X bar is equal to X bar 1, maybe 4.51 or something. X bar 2 is equal to 4.73 or something. Then we can calculate this 100 times. Then we estimate the distribution of X bar. Then we have some histogram. then we can get the standard deviation of this. So we can get maybe standard deviation of X bar. Then that is 0.254. So this is slightly small because of two reasons, but at least this is reasonably close to this answer. Okay? And why this is slightly small? The one reason is this is just a simulation. So if we try once more, maybe that becomes 0.28 or 0.27. Okay. And another reason is that we only have 5 observations, and sometimes we sample the same observation multiple times. So that actually they underestimate the this standard deviation. In reality, if we observe more values, suppose these 5 are the weight of newborn babies in kilogram, then if we observe more values, actually we never have the same value. Maybe we get 5.4 or maybe 5.18, but we never observe exactly the same value the multiple times. So actually that underestimate so that feature underestimates the standard error of X bar. So this is slightly small because only we have 5 observations, but still we get pretty good estimate. If we have 20 observations in the data set, it's really very accurate. Even 5 observations, they're pretty reasonable estimate approximation. Yeah, so this is the theory. So just we can calculate it theoretically, but this is for very limited case. Yeah, so that is what we explained. Do you have any questions about bootstrapping?
It seems to make sense.
Yeah, great. Yeah. And the coding is also not that difficult. Yeah. Some coding is necessary, but yeah. And some of the package, such as boot package, maybe some other package, have the bootstrap procedure. Yeah, so we have just had one example about bootstrapping to estimate the standard deviation of X bar, but now that we think about a little more complicated case. So this is an estimation problem. So we want to estimate the y is equal to alpha plus beta x. Maybe we use the different notation, maybe the omega plus alpha x. Then we want to estimate how reliable this alpha is. And the original data set is here. So this is very simplified example. So only 3 observations to estimate linear model. Then we bootstrap. So 3 observations. So 1 randomly sampled observations are maybe 3, 1, 3. Maybe another one is 2, 3, 1. Another one is 2, 2, 1. Then we have different data set, and we can get different omega hat and different alpha hat. And we just calculate the alpha hat here from this data set. And we do the same thing for this data set. This data set, we do this b times, maybe 300 times. Then we can get the distribution of alpha hat, maybe histogram of alpha hat. Alpha hat star here, asterisk. Then we can evaluate variability. For example, we can estimate the mean. Mean is actually just usually almost similar to alpha hat from original data set. But also you can calculate standard deviation since we have distribution. Yeah, and okay, but the linear model still, we have a way to estimate the standard error of alpha hat. Right? So basically matrix form if the X prime, X transpose is the design matrix. Basically, this estimates the standard error of omega hat and the alpha hat. The covariance matrix is estimated by this. So why we need it? But actually, in some complicated case, the bootstrap is really needed. For example, here. So suppose that there are 200 observations for response time to signal and alcohol content in blood. So we are thinking about the 200 drivers response time to signal when they intake some alcohol. And but some observations come from the same person, so that there are only 82 persons. So this data set is pretty complicated, right? We have 82 persons. Maybe some persons have maybe 3 observations in this data set, but some persons only have 1 observation in this data set. So in such a case, at least those observations are correlated. Observations within the 1 person is correlated. So we cannot say 200 observations are independent. Right? So we cannot use the linear model theory to estimate the standard error of alpha hat, beta hat. So how to deal with this? In this case, 82 persons are independent persons, usually we assume. So we bootstrap 82 persons with replacement. Then we estimate this model, regression model. Then we repeat this again and again. Then we get the estimate for alpha hat and beta hat. So this accounts for correlation within the persons. So it is a fair estimate for variance of alpha hat and beta hat. This can be very complicated if you derive this from the mathematical, the assumption of the model. So in this case, usually we bootstrap. We use bootstrap to estimate. And this is very typical example in the medical data. That we have 200 patients data, but actually some patients visited that office multiple times. So yeah, only 82 persons are in the data set. And always I bootstrap. Of course, some mathematical model, statistical model exists to deal with this situation, but considering the statistical model is more complicated. If there is a one-size-fits-all methods such as bootstrap, then that is much more convenient. Yeah, so that is chapter 5. Okay, so next time we do some exercise on bootstrap. Do you have any questions?
Not this time.
Great. Okay, so if not, see you on Wednesday.